Welcome to this course on transition metal organometallics in catalysis and biology. We have been talking about olefin polymerization in the last few lectures, and in this regard in the immediate past few lectures we have focused on the development of Ziegler-Natta catalyst, particularly with respect to polyethylene as well as polypropylene. In this regard, let me just briefly talk about the highlights of what we have covered so far. In this context, the first we spoken about is ethylene, TiCl4 25° centigrade, 1 bar pressure. This is Ziegler-Natta catalyst. Gives polyethylene, and this is under heterogeneous conditions. Produces HDPE of molar masses 10 to the power 4 to 10 to the power 5 Dalton. Subsequently, we saw that for polypropylene, it gave isotactic polypropylene or IPP, and this is also heterogeneous, and this also has head to tail linkages. The first in this advance focusing more on polypropylene, the first catalyst for polypropylene was Cp2 titanium dichloride with Et2Al Cl. This is this is for polyethylene, sorry. Ethylene, this catalyst is homogeneous homogeneous, but lower activity for ethylene and no activity for alpha olefin. So, and this was reported by Nata. So, the first homogeneous catalyst was reported by Nata. Then subsequently Kaminsky produced Cp2 zirconium Me2 MaO. So, for polyethylene homogeneous and extremely active 500 kg of PE polyethylene per millimole of zirconium per hour. So, post this, what was reported is the fifth one, which is Cp2 zirconium pH2. So, Cp2 titanium pH2 MaO and this ethylene En THIND zirconium Cl2 MaO. This we had discussed that is again homogeneous and was producing 43,000 kilogram of polypropylene per mole of zirconium per hour. So, what we the point to note is that this is sort of timeline of development. So, the first is heterogeneous for polyethylene, then heterogeneous for polyethylene, and then first homogeneous came with this BCP system, homogeneous for polyethylene. Now, this BCP system with MaO gave extremely high activity of polyethylene per millimole per hour, and then subsequently BCP system with MaO and this ANSA system with MaO gave extremely high isotactic polyethylene per hour. And we had looked at this system, this ANSA system in much more detail in our previous discussion. So, and what we saw that as we move from homogeneous to heterogeneous, in these cases the catalyses are, as we move from homogeneous to heterogeneous, this is multi-site for this heterogeneous and heterogeneous, and for the homogeneous ones these are all homogeneous, these are single site catalysis, and this single site catalysis means that polymer has narrow polydispersive index and low PDI, and polymers are much more well behaved in terms of their properties. So, let us now focus on this ANSA complex that we had discussed, which has extremely good activity for polypropylene. So, this ANSA complex EN THIND zirconium Cl2 MaO, structure wise the complex looks something like as it is shown over here. Maybe the structure as is shown over here. This is bound to zirconium with MaO. So, this is the structure of this complex, and the ratio of these two MaO is about MaO can be represented as AlO methyl. So, this ratio is 1:300, means large excess of MaO is required. And then the question comes that what is the role of MaO? The question subsequently come is what is the role of MaO? It seems like that MaO is a magical reagent which enhances the activity of this catalyst, this homogeneous catalyst, to the extent that it even surpasses the original heterogeneous Ziegler-Natta catalyst. The answer to that is that MaO has three functions. MaO has three functions, that MaO acts as a methylating agent, that MaO acts as a methylating agent. That means that these halides get replaced to becoming methyl. So, they convert zirconium halides to zirconium methyls, and second function is that it has a Lewis acid carbanionic acceptor, Lewis acidic acceptor. This is an important function of MAO. The first is it is methylating it and then making it dimethyl, and still there are large excess of MAO which are highly electron deficient Lewis acidic species. Now, after they have methylated the halide, they abstract one of the methyl. So, it is not only a methylating agent, but also it is a methyl anion acceptor. So, that is why it is called this carbanion acceptor. So, not only it is making methylating it, converting halide to methyl, and then subsequently it is also accepting abstracting the methyl, snatching the methyl. And the third role of MAO is that and serve as a counter anion to zirconocene cation. So, it has 3 role and this can be suitably explained in this series of chemical equation as is shown below. For example, Cp2 zirconium chloride methyl MAO so methyl. So, this is the first function that we had seen, the methylating agent. Now, the second function is that it acts as a methyl abstraction. So, this can be represented as methyl with MAO giving Cp2 zirconium. One of the methyl gets abstracted, the other is a vacant site plus. So, only one methyl gets accepted and then ends up becoming a vacant site over here, and then the anion. So, this is the second role. This is the what portrayed out here is the second role of methyl abstraction, and then this methyl group ends up in the carbanion of MAO as is shown here. Al Me O N Al Me O. So, this methyl group which gets abstracted from here ends up on the aluminum as is shown here, and then both the second and then subsequently this acts as a counter ion to this zirconocene cation, and what happens subsequently is in this vacant site the polypropylene lands up, occupies polypropylene comes and Cp2 zirconium methyl this cation and MAO minus anion, which undergoes insertion subsequently with many propylene as it is shown to give isotactic polypropylene. So, the role of MAO is greatly explained, that it has three. First is it works as a methylating agent. So, this gets converted to methyl. Second, it has a anion abstractor. So, one methyl gets converted, gets abstracted, and then there is a vacant site hole, and then subsequently to this hole the olefin comes, binds, and so this now serves as a non coordinating anion, non coordinating anion, with low charge density. So, this is a interesting observation that this MAO has several roles, and after abstraction what is possible is that it stabilizes this zirconium 2 species cation, zirconium cation being a non coordinating anion with low charge density. Now, what it sort of implies that this can be achieved with any other non coordinating anion with low charge density, and that should also be equally effective. And the ingenuity of organometallic chemist comes into play, where indeed such a well behaved catalyst were developed with other non coordinating anion, and which were extremely good for polymerization. So, this shows how the structure activity relationship, how understanding helps in developing the catalyst, or helps in improving the catalyst, and this is done by Tobin Marks, professor of Eastern University, who had used a non coordinating anion to develop this zirconium species, which is extremely active. So, what Marks did is he took this Cp2 zirconium dimethyl and used this Lewis acid of boron. So, now instead of aluminum it is boron C6F5 whole 3 in pentane gave Cp2 zirconium methyl the loosely interacting with CH3 B C6 F5 whole 3. So, this is a ion pair separated species with zirconium being in positive and this boron being negative. After abstracting this methyl from zirconium methyl, methyl, and this was contribution, this famous nice example was reported by Marx in 1991, and this complex, this cation take complex resembled the MAO analogues in catalytic performance, and this was structurally the catalyst was structurally characterized and is rightfully designated as a single site catalyst. So, this was a fantastic improvisation made by Mark, where he development a replacement of MAO using this boron trifluorophenyl reagent, which abstracted one of the methyl and also behaved as a non-coordinating anion in stabilizing this zirconium Cp methyl cation, which carried out the polymerization of polypropylene with equal efficiency as that of the MAO counterpart. So, that this shows how understanding a suitable, a proper understanding of the catalyst mechanism helps in improving the catalyst greatly, and that is why the structure activity relationship is so important in developing the efficiency of the catalyst. So, with this I come to the conclusion of today's lecture, where we have seen how this catalyst for polypropylene improved from the heterogeneous Ziegler-Natta titanium tetrachloride diethyl aluminum chloride based catalyst, multi-site catalyst, to the focus shifted towards developing single site catalyst that were advantageous, but the inherent difficulty of this homogeneous single site catalyst was their activity was inherently low, which was however overcome by advent of MAO by Kaminsky in 1981, and subsequently even MAO got replaced by contribution from Mark, who could develop better similar catalyst bearing boron based non-coordinating anion, where the boron triphenyl pentaphenyl C6F5 the moiety C6F5 moiety could act as serve as a methyl abstraction as well as non-coordinating anion and stabilize this a single site catalyst. So, with this I come to a conclusion of today's lecture. We are going to be looking at this catalyst development and some more interesting aspects about how to achieve the symbiotoxicity, isotoxicity at will, and the rationale that went in developing this catalyst as we discuss the topic in more detail in the next lecture. Till that time, goodbye, and thank you for being with me in this class. See you in the next lecture.